In this lesson, we're going to be discussing the sigma notation, and we're going to look at how a series can be represented using the sigma notation. Now, first of all, what is a series? A series is, in fact, the sum of the terms of a sequence. So if we have a sequence where we list its terms by U1, U2, U3, etc. Now, the series would in fact be the series corresponding to that sequence would be the sum of the terms of that sequence. And in fact, sequences are represented by general terms. In case there is a certain pattern that relates the different terms of the sequence. For example, here if we could have a sequence represented by the general term un equal to 2n plus 3. So for n equals to 1, the first term of the sequence is 5. For n equals to 2, the term of the sequence for n equals to 2 is, in fact, 4 plus 3, which is a 7. For n equals to 3, so the third term of the sequence for n equals to 3 would be 2 times 3, which is a 6 plus 3, that's a 9, etc. Now, these are the terms of the sequence. However, the series corresponding to that sequence would, in fact, be consisting of the sum of 5 plus 7 plus 9, etc. Now, in order to represent this series using the sigma notation, now as you can see here, the sigma is represented by the capital letter sigma of the Greek alphabet, which you can find here. And inside sigma, you would actually find the general term of the sequence. Now, over here it says in terms of r. However, over here I've written the general term in terms of n. Now, that is a parameter. You could, in fact, name it whatever you like. If the general term here is in terms of n, then the values of the parameter here would be in terms of n as well. So, in fact, over here, if I were to represent this series using the sigma notation, now inside should go the general term of the sequence. Since over here it says in terms of r, I'm going to replace n by r, so that is 2r plus 3 inside sigma. And over here, this is the range of values consisting of the parameter. So it really depends on how many terms I'm adding in the sequence. Okay, so the first value of r, the first value of the series here, which corresponds to r equals to 1. Now, over here for r equals to 1, I have the first term of the sequence, and I'm starting my sum there. So this is why here it would in fact start from r equal to 1. So I'm indicating that this general term of that series, I'm starting the sum for r equals to 1. And then I need to stop that sum at some point. So the upper bound of the range of the parameter stops the sum at that specific value. If I wish to add the infinite terms in that sequence, then the upper bound would in fact be infinity. So I would know that the infinite terms in that sequence are being added in this sum here. However, if I wish to add the first 5 terms of the sequence for this series, then r would go from 1 to 5, because from 1 to 5 I have 5 terms. So over here, in fact, I would be adding, so that would be equal or corresponding to, for r equals to 1, I have 5. For r equals to 2, I have 7. For r equals to 3, I have 9. Now for r equals to 4, I still need 2 more. For r equals to 4, that's an 8 plus 3, which is 11, and then the last one would in fact be 13. So since I stopped the sum at the fifth term of the sequence, then in fact this series would be corresponding to the sum of the first 5 terms. Now, however, the range of the parameter does not necessarily have to start with the first term. It really depends on what you wish to add. If you start r by 3, from 3 to 5, then in fact you'd be adding these 3 terms, starting from the third term, then adding the fourth, then adding the fifth. Now, this is a general idea on how we deal with the sigma notation to represent a series. Now, in our next, on our next slide, we have two sigma or two series represented by their sigma notation to in fact expand. So to expand a series when written in a sigma notation, it means that I need to in fact represent it this way using the sum of the terms. Now it doesn't say, sorry about that, I moved way ahead. So over here the question does not say expand and evaluate. Evaluate means give the final sum, give the value of the sum. However, expanding is just listing the terms in that series to add it. However, if it says expand and evaluate, in that case, you'd need to expand sigma, list the sum of the terms, and then give the final sum. However, they're not asking us to evaluate the sum here, so we're just going to expand. So r goes from 1 to 5 here, so we just list the terms, the first 5 terms of that series or that sequence, and just add them. So for r equals to 1, I have 3 plus 6, which is a 9, plus, because it's a sigma, it's a series, so the terms are being added here. For r equals to 2, 6 plus 6, that's a 12. For r equals to 3, that's a 9 plus 6, which is a 15. And then for r equals to 4, I'm going to end up with 18. And for r equals to 5, I'm going to end up with 21. So this is the first series expanded. If I were to be asked to evaluate, then I would in fact give what this sum is equals to. However, since the question just says expand, we're going to stick to expanding the series here. Now, in this second one, r goes from 1 to infinity. So over here, we're adding the infinite number of terms in the series. So usually infinite sequences or infinite series are usually represented by listing the first few terms and then including an ellipsis at the end, like the 3 dots, to say that this goes on infinitely, or this pattern goes on infinitely. So I'm going to start with the first 3 terms. I'm going to just drop this down the line. So for r equals to 2, r equals to 3, and then start evaluating them. So I'm going to determine the first 3 terms of the series and then eventually end with an ellipsis to say that this series goes on infinitely. So over here for r equals to 1, negative 1 to the 1, that's a negative 1, times 1 squared, which is 1. So the first term is negative 1. For r equals to 2, negative 1 squared, that's a positive 1, and 2 squared, that's a 4. So this is a 4 here. And then for r equals to 3, negative 1 cubed, that's negative 1, and 3 squared, that's a 9. So over here, I should have a negative 9. And then include the ellipses in order to say that this goes on infinitely. And the more terms you include before the ellipses would help you, in fact, see the pattern of the series or the sequence better. Okay? Now in this example, we're going to write the following series using the sigma notation. So here I have the series and I wish to represent it using sigma. So As we've mentioned before, in order to represent a series using the sigma notation, I need to, in fact, determine the pattern by which the sequence is progressing. So if I consider that I have here, this is the first term for n equals to 1, this is for n equals to 2, this is for n equals to 3, for n equals to 4, and for n equals to 5. So I know that this series is in fact adding the first 5 terms of its corresponding sequence. So the range of values of the parameter, which I called n here, is from 1 to 5. So I know I will be representing this by a sigma where n goes from 1 to 5. Now I need to determine the general term, and the general term is what in fact highlights the pattern by which the terms of the sequence or the series are progressing. Okay, so I notice here that to move from -3 to 5, I'm in fact adding 8. And then you notice that for following each term, in order to determine the next term, I'm still adding 8. So usually whenever you're adding a constant term, that is in fact an arithmetic sequence. And we know that the general term of an arithmetic sequence is represented by a linear expression in the form an plus b. Okay, linear, which is a polynomial of degree 1, where the variable is in fact the parameter used in the sequence. So a times n plus b, that's the linear expression, so I know that this is the general term of that sequence. So usually the gradient of the linear expression represented here by a is in fact that constant we're adding, which we call the common difference of the arithmetic sequence. So over here, since I'm adding 8, then a is equals to 8. So I know it's 8n plus b. I still need to determine what b is. So in order to determine what b is, I could just choose any of the terms in the sequence. I know that for n equals to 1, the first term is -3. So for n equals to 1, that's an 8 plus b, which is equals to -3, which gives me b equals to 11. So I know now that b is equals to 11, and we can check that for the remaining terms in the series. For example, for n equals to 2, 8 times 2, that is 16. I'm sorry, this is a -11. So over here, we're just bringing 8 to the right-hand side of the equation, so it's -8. So over here, sorry, it's -11. So it's 8n minus 11. So do you see the power of checking? Checking your answers is really something powerful and needy to do, because when you check your answers, you can figure out some calculation mistakes that you've made. So over here for n equals to 2, it's 8 times 2, which is 16, and 16 minus 11 is a 5. 8 times 3, that's a 24. 24 minus 11 is a 13. So now I'm pretty sure that I have the correct general term, and make sure to include it inside parentheses, especially if you're adding terms inside the general term of the sequence or the series. So over here, it's 8n minus 11. If you've used an r here, then it would be an 8r minus 11. If you used a k, then it would be an 8k minus 11. So this is the first series represented using its sigma notation.